Here we're in little Nellie Newton's gym, where she's getting ready to do some acrobatics. Nellie hangs onto a metal ring that is suspended by 2 strands of rope that are attached to the ceiling above. Why is Nellie smiling? She's smiling because she's learning physics, conceptually. I want to show you 2 ways to determine which rope, the left side or the right side, has the greater tension. First, let's draw a horizontal and vertical axis for the point of interest, the center of the ring in which the force vectors converge. We begin by assuming that the tension in the right-hand rope is this. This vector defines the scale at which the other vectors can be compared. Then the violet vector is the horizontal component of that vector. Since there's no change in motion, the left-hand side must have an equal and opposite horizontal component, like this. Extending our white dashed reference line, we see that the vector for the left-hand rope has this length, longer than that for the right-hand vector. So tension is greater in the left-hand rope. And we can go further. Let's draw the vertical components of both vectors. The addition of these 2 vertical components will be equal and opposite to Nellie's weight, which we show with this red vector. So our complete vector diagram looks like this. Now another way to approach the problem, the parallelogram rule. We'll begin with a reference vector that represents Nellie's weight. Then we know that the 2 tension vectors must have a resultant equal and opposite to Nellie's weight, this dashed vector. Completing the parallelogram defined by the angles of the ropes, our vector diagram looks like this. Again, the longer vector for the left rope shows tension in the left rope is greater. How much greater? Since the vectors in either case are to scale, we see that the tension in the left rope is somewhat less than Nellie's weight, about 8/10 her weight, and the tension in the right-hand rope is about half her weight. Although the first vector component method nicely lends itself to trigonometry calculation, you might agree that the parallelogram rule is simpler. It's nice that physics makes use of a variety of methods in solving problems. Let's return to Nellie in a different situation. This time she holds the ends of a rope that is draped over a large pulley, which in turn is fastened to the ceiling. Note it's a single strand of rope. What we wish to know is how does the tension in each strand of the rope compare with Nellie's weight? Let's focus on the system outlined by this box. Whatever occurs outside the system is immaterial. Inside the system of Nellie and the supporting strands of rope, the sum of the rope tensions and Nellie's weight cancel to 0. Nellie is in equilibrium. We show and label the appropriate vectors. From the equilibrium rule that states that all the forces acting on a system in equilibrium cancel to 0, we see the tension in each strand is half her weight. Never mind the overhead pulley, and never mind that the 2 strands are both ends of the same rope. They aren't relevant. In any problem, first define your system. I want to leave you with a question. By way of strings and pulleys, a pair of 10 Newton blocks pull on a scale as shown. What's the reading on the scale? Think about that. Until next time, good energy.